So the work you did compressing the spring was positive 1/2 kx squared. You pushed on the spring, and the spring went in the direction that you pushed. But the work the spring did was negative 1/2 kx squared, because the spring pushes in the opposite direction of the displacement. That produced that cosine of 180. So do I need to review that, or do you remember that from yesterday? That good enough? Good. We're going to define potential energy. The change in an object's potential energy equals minus the work done by the conservative force. I'm trying to choose my words carefully, but I also want to make sure that you have kind of an understanding of why it's done this way. This is a choice. When we talk about potential energy and we talk about the storage of energy, we as a culture of scientists have decided to frame this from the standpoint of the conservative force. In this case, the spring represented the conservative force. The work done compressing the spring is how the object and system's energy changed. But because that worked out to be negative, because the spring was fighting not to be compressed, we say the change in potential energy is the opposite of that work. So the change in elastic potential energy for the system of a spring being compressed by a mass is equal to 1/2 kx squared. We say that energy is now stored in the system, and that system represents the object, the spring, and whatever is necessary to hold the spring in place while it is being compressed. And that's the system. If this wasn't here, the spring never would have compressed. There would have been no energy stored. Right? The whole thing is required. And obviously, without the spring present, there's no energy stored. So there is a system in place. The energy is stored in the system. The energy is not stored in the object. That seems like a distinction without a difference, but it has at least important ramifications later. One of those ramifications is going to be when we start talking about gravity from a universal perspective. So for right now, I just need you to understand that all forms of potential energy require the interaction between your object and something else. In this case, the spring, and whatever's holding the spring in place. Now, I want to add to this today and try to develop a little bit more information. And what I want to do for that is a relatively easy idea. At least I hope that it is. We'll see if it actually works out that way. Let's consider you in a box. There's his arms up higher there. There, you in a box. And your job is to lift the box and put it on top of a shelf. Simple enough idea. You can do work on the box, and at the same time, gravity will do work on the box. Let's say, for our argument's sake, that we're going to lift the box from the ground upwards a distance h, representing the height of the cabinet. And you're going to lift the box with the smallest force necessary to lift it. Could you take a moment and calculate the work done by you and the work done by gravity? This should be very straightforward. I'm not trying to make this hard. We've talked about forces before. Assume that you are applying an upwards force that will successfully lift the box and that you're using the least amount of force necessary. Let's say the box is mass m. Again, to answer Gabby's question, we want to provide an upwards force. That is the minimum force necessary to lift the box, but the box isn't going to accelerate. So that means the net force on the box is going to be 0. I think it's pretty easy to figure out how big this force has to be then, correct? Is there another force acting on the box? Really? No, nobody can say yes or no? Yeah. And what is it likely to be? All right, so we have 2 forces that act on the box, one upwards, one downwards. How big is the downwards force? So the upwards force has to be the same size as the downwards force. Not hard. The minimum force necessary to lift a box is pushing up with the weight of the box. Again, not trying to make this hard. I think these are easy questions. Maybe you're used to me asking you harder ones. Don't worry, they'll come in. I think then that the upward force would just be mg. This is how hard I push upwards. Times, well, delta x. That's going to be how high, right? We're lifting at h. And then the cosine of the angle between those two. 0. I'm lifting the box up. The box is going up. Pretty straightforward. Looks like the amount of work I do is equal to mgh. Amount of work done by gravity, well, mg again, right? The box still travels up. How are these different? Sure, cosine of 180. Box goes up, but the force was down. These produce the same answer, but they have slightly different connotations. You are an external force to the system. You caused the box to go upwards. You're external to the system. I want to point this out. The system is the box and gravity, but you are external. If you had not shown up, the box would just sat on the floor, correct? You're the agent. You gave energy to the box. The problem is that the whole time you did that, gravity was acting against your motions and was, I'd say, taking that energy away. But we know that once the box has actually been delivered, that box is on the top of the shelf. It could at any time fall off the top of the shelf. And in so doing, gravity will pull the box to the ground, increasing its velocity, delivering work. We recognize that the amount of work done by gravity could be stored for later use. I could leave the box up there at the top of the shelf, but at any time just push it off the top of the shelf and it'll fall to the ground. That will change the kinetic energy of the box. It's going to speed up, correct? And we know that that energy of motion is directly applicable to kinetic energy. So we've defined the change in potential energy of the box to be opposite the work done by a conservative force. You lifted the box, but you changed the earth box system. You separated them. So again, you lifted the box, but you changed the earth box system. This stored energy in the form of what's called gravitational potential energy. The amount of that energy is just equal to mgh. This is a complicated way to say it. And when we actually start using this property, we'll find that it's relatively simple. But you have to understand, the energy isn't with the box. The energy is in the fact that you separated the box from the earth a small amount. And that the earth will pull the box back eventually. That means any time an object is lifted, the object has energy related to its interaction with the earth. And that energy is based more or less on how high the object is. Now, I don't want to make this a bigger deal than it is, but there's some stuff that I need to make sure you have in your notes. And one of them is I want you to kind of redefine this a little bit. You guys see that battery sitting on the edge of my desk? It looks like something old. It's a lantern battery, a 6-volt lantern battery. It's perched right at the edge of my desk. It is unlikely that it will fall off my desk, right? The desk is nice and level. It's been sitting there for the last couple days. I feel confident that if I leave tonight, come back tomorrow, it'll probably still be there. Does the battery really have gravitational potential energy? I'm asking this not as a means of tricking you. Because I could point out that the battery is above the floor, true enough, by about 1 meter. So if I want to define how much potential energy the battery has, do I define it relative to the desk or relative to the floor? Or relative to the first floor? When we talk about the H here in MGH, we're talking about the potential of the object to change its height. That's why the word potential energy is used here. If I don't think the battery is ever going to fall off the desk, I would never say that it has energy relative to the desk. I'd say there's no energy there because it's not falling off the desk. But if it is going to fall off the desk and hit the floor, then I could say it has potential energy relative to the floor. Gravitational potential energy is a relative measure. We set the baseline that we're going to call 0. We have to be careful about this because we have to decide what's the functional use of knowing the object's potential energy. There is a functional use here. There's a reason why we want to know the object's potential energy. But if the object never leaves the desk, then it really doesn't have any useful energy for us. I mean, everything in this room had work done on it to be brought into this room from the first floor. Somebody lifted it all up. But if it never falls to the first floor, do we say that it has more energy now because it's in this room? Again, it doesn't make functional sense. A spring is a little different because you press something against a spring, you let go, the spring is going to release the object, it's going to shoot across the room. But for gravitational potential energy, we don't have what is considered an absolute 0, a baseline. The spring sitting right there is easy to see, it's right there in the front of the room, that there's no real energy stored in there. Right? We know what its 0 looks like. I hang something on it, then it would have some energy stored in it, but right now it doesn't. But when it comes to gravitational potential energy, we need a functional 0, something that we know is useful in our problem. Now you're wondering, what will these problems look like? Here's a simple idea of a simple potential energy problem. Let's go back to my battery sitting on my desk. Let's say that, as it so happens, somebody inadvertently, precariously purchased it right on the edge of the desk. My desk is 0.85 meters above the ground. Now, I could ask you, how much potential energy does the battery have relative to the ground? It is 1.5 kilograms. So if I tell you that it's a 1.5 kilogram battery and that it's perched 0.85 meters above the ground, you have a functional way of figuring out how much potential energy it has relative to the ground. It's a way of figuring out the potential energy relative to the ground. Now the question is, well, when would that be useful? And here's what I want you to understand. It would be useful if I wanted to figure out maybe how fast the battery's going when it's been knocked off my desk and is falling towards the ground. Work's being done on the battery by gravity. It's losing potential energy. Where's that energy likely going? Is the battery moving? The battery's moving. There's likely an exchange being made between potential energy and kinetic energy. That exchange is 1 for 1. For every joule of potential energy lost by the battery must be gaining a joule of kinetic energy. Now, this concept that energy is finite is called conservation of energy. It can be proved, but the proof is largely ornamental, meaning I could do a proof, but you'll never probably do the proof again on your own. I want you to understand that we can use this functionally. If we have a system where the energy remains constant, then the energy goes from one form to another, but the total amount of energy stays the same. So there's important questions here and important distinctions. Last example here. this object is falling, then there is a change in the potential energy of the object. This means that work is being done by gravity. It's reducing the object's potential energy. That's the negative sign. The object's getting closer to the ground. That also means that since this is the only force acting on the object as it falls, that it is a net force, and it is causing a change in the kinetic energy. Now, this derivation is not necessary that you know how to do this. The result is delta U is U final minus U initial. Delta K is K final minus K initial. That negative sign is the correlation between work by a conservative force and the change in potential energy. I don't know if you see this here, but if I distribute that negative sign, I get that, don't I? I'm going to move this to the other side. Move this to the other side. Now, this is the sum of the energy at some point in the future. And this is the sum of the forms of energy at some point in the past. It clearly says that if your only interaction is that with a conservative force, then the energy before has to be equal to the energy after. All right, folks. You currently have 3 forms of energy in our knowledge base. We know that kinetic energy is the energy of movement. We have 2 forms of potential energy that require the interaction with an object. We have elastic potential energy from a linear spring. We have gravitational potential energy, which requires the consideration of a baseline. These 3 forms of energy can be manipulated by doing work. Work is the method that you can change something's energy. When I, an external object or external agent, do work on a system, I can fundamentally change one of these values or more than one of these values. If I'm doing that work from a constant force, then I don't have to do the integral. For those circumstances, I can just use the force as a constant. It's important to understand that potential energy is not defined by the agent, it's defined by the work done by the conservative force. So I have to recognize that and can keep that as part of my knowledge base. These are all the things we've talked about the last couple days, but there was a week off, so I'm tying them all together. Don't forget that the amount of work done is highly dependent on how much of the force was directed in the direction of the displacement. That's why I have all those vectors there and the big dot there to remind us that this is a dot product, and the dot product involves the cosine of the angle between them. Good so far? Now, I want to consider this for just a moment. If work is being done by a net force, we know that this can change something's kinetic energy. Right? We talked about that. That's the work energy theorem. If an object is falling